Welcome to lecture 32, in which I continue my discussion of the quantum field theory setup for fermions. Recall that in lecture 30, we calculated the quantum mechanical partition function as a fermionic path integral over the Grassmann fields C star and C of this object here, which involved the Hamiltonian. The Hamiltonian function that we had here was the expectation value of the Hamiltonian operator that was built out of the ladder operators A dag and A. Also recall that in the last lecture, we considered the Dirac field equations ID/-m psi 0. This lecture, we will combine these two results from these past two lectures and construct a Hamiltonian for the Dirac field that then will give us a path integral definition for these fermions. To get started, recall that in lecture 22, we constructed a Lagrangian density for a complex scalar field phi based on the symmetry, such as Lorentz transformations. While we can employ this same strategy for the Dirac field, there is a quicker way to get to the same result. To do so, notice that in lecture 23, we found the equations of motions for the complex scalar field phi and its complex conjugate phi star, which we treat as independent components. For the Dirac fields, we have the equations of motions, which are just the Dirac equation. So we're gonna work backwards to get the Lagrange density from the field equations. If we have a complex field such as the Dirac spinor psi and its Dirac adjoint psi bar, and we treat these two as independent components, then from a given Lagrange density L, the equations of motions are given by essentially the same formula that we had for the scalar fields in lecture 23, except that we exchange all the fields phi with respect to the fields psi and psi bar. Now, these equations of motions that we get for given Lagrange density then must correspond to the Dirac equation given in 32.3. It is not hard to figure out what the Lagrange density has to be that gives rise to the Dirac equation from this equation 32.4 here. It is given as psi bar ID/-m psi. If you plug this back in, you find the Dirac equations of motion. Having the Lagrange density, we can construct the Hamiltonian density H simply by the definition that H has to be the conjugate momenta times the time derivative of the field minus the Lagrange density. Here, the conjugate momentum pi is defined as the derivative of the Lagrange density with respect to the time derivative of the field, which, using this Lagrange density in equation 32.5, gives rise to psi bar I gamma 0. Since psi bar was defined as psi dagger gamma 0, we can use the fact that gamma 0 squared is just unity to find that the conjugate momentum is just I psi dagger. Plugging this in the formula for the Hamiltonian density, we find that the Hamiltonian density is given by this expression here. And from the Hamiltonian density, we then find the Hamiltonian as the integration over space of the Hamiltonian density, which then is the integral over space of this function that we had before. Here, the fields psi and psi bar are thought to be classical fields. They are fermions, but they are classical. And the fact that they are fermions can be treated under quotes classically through taking them to be Grassmann variables. They are anti-commuting. If we would quantize the theory, then the fermionic fields would correspond to some operators, such as the ladder operators, that we had in our earlier example for the Hamiltonian density of fermionic quantum mechanics. Also, the form of the Hamiltonian that we have here in 32.9 is very much reminiscent of the form of the Hamiltonian given in equation 32.2, except for the constant term in this first equation here. Long story short, if we have this Hamiltonian for the Dirac field, we are going to identify the classical but anti-commuting fields psi dagger psi with the Grassmann variables C star and C, such that we have an expression for the path integral. So we find that the following result, for the path integral for a Dirac fermion. It's given as the integration over the classical anti-commuting or just Grassmann variables psi dagger psi of e to the minus SE, where SE is this expression here. It's just the Hamiltonian that we wrote down before. And we are going to call this the Euclidean action the same way that we have called the corresponding quantity the Euclidean action in the bosonic field theories. As in lecture 5, that is just enabled because we are going to just introduce this label tau as the continuous variable that strings together the individual entries I in the path integral formulation. The main difference with respect to the bosonic case is that in this case, for the fermionic path integral, the fermionic fields are antiperiodic in Euclidean time. This means that the field evaluated at tau is beta is equal to minus the field evaluated at tau is 0. Some more definitions. We can define the Euclidean Dirac matrices in the following form. So we're going to use the label E for Euclidean, and we're going to define them such that gamma 0 E is the same as the Minkowski gamma 0 matrix. And the spatial Euclidean gamma matrices are minus I times the Minkowski gamma matrices. If we do this, then the Clifford algebra for the Euclidean Dirac matrices is such that the anticommutator of the gamma matrices gamma A and gamma B is twice the Kronecker delta, or the Euclidean metric, times the unity. And these Euclidean matrices also have the property that they are Hermitian. Using this definition involving these Euclidean Dirac matrices, we can write down the Euclidean Lagrangian density LE in this following form. And finally, since the spinor psi dagger and psi bar only differ by a constant, namely the matrix gamma 0, the Jacobian from changing d psi dagger to d psi bar is also just a constant, which we can again sort of absorb in the overall constant that's multiplying the partition function. So if we ignore this constant for now, we can write down that the partition function for the fermionic quantum field theory is given as the following expression here, where psi is taken to be the spinor field corresponding to a Dirac fermion. Next lecture, I will tell you how to evaluate this expression for the fermionic Dirac, for the free Dirac fermion, and eventually we are going to discuss interacting quantum field theories with fermions as well. And this concludes the present lecture.